This is a little revision lecture about basis of a topology. So recall the following theorem from lecture notes about two bases of a topology. Yeah, maybe first recall that a set can have a lot of different topologies, and some of those topologies could be finer or coarser than other topologies. Some could not be, may not be comparable, and so on. So it is a complicated situation. And one of possible methods to define a topology is to construct a topology from a basis. But then two different bases could happen to define the same topology. And the theorem says that two bases define the same topologies on some set, if and only if every set that is open with respect to B1 is going to be open with respect to B2 and vice versa, right? So if it is open with respect to B2, then it is also going to be open with respect to B1. Now, the proof of this theorem is one of the exercises in the problem set. So I suggest that you either try to do it by yourselves or you just read the official solution that some of you have already submitted. Now I'm going to just give you maybe one example of a theorem that was not explained or in class, right? So yeah, in class I was talking about disks versus diamonds versus rectangles, how they all define the same standard topology on R2. So in my example now, I'm going to introduce two somewhat exotic bases of a topology, and then I'm going to show that they define the same topology on R. And this is the standard topology. So the first basis consists of all open intervals from A to B, where A and B are rational numbers. So this is the basis of a topology on R. It is straightforward to verify that both axioms of a basis hold, so it is indeed a basis. And notice that A and B are rational numbers, so these basis only contains finitely many open sets. Okay, so the second example is somewhat strange. So here we're going to consider all sets of the following kind. So x minus epsilon, x plus epsilon. So an interval from x minus epsilon to x plus epsilon, the union of an interval from x plus 2 epsilon to x plus 4 epsilon, and with the interval from x minus 4 epsilon to x minus 2 epsilon. Right, so geometrically, this looks like the union of three intervals. Each of them is of the size 2 epsilon, and so they're centered at x. So the size of each of them is 2 epsilon. Wow. I mean, you can try to directly verify that these are indeed bases of a topology. But now let me explain why. And notice that, so here x is a real number and epsilon is also a real number. So the second basis is uncountable because every set in the second basis is kind of, it corresponds to the choice of two real numbers. So it is uncountable. And they still define the same topologies, which is the standard topology on R. So to verify it, we need first to check that every set that is open with respect to the first topology is also going to be open with respect to the second topology, which boils down to verifying that every basis set with the first topology is open with respect to the second topology. So we need to verify that every interval from A to B is going to be open with respect to the second topology. How do we do that? So we take an interval from A to B, so this is a real line. Then we choose any point here. Let's say that this is going to be, this is going to be a point X. So this is X. And then we need to show that there exists, so that this interval from A to B is open with respect to the second topology, which means that we need to show that there exists a second basic set that sits entirely in the interval from A to B. That is, well, a basis set with respect to the second topology, right? So maybe let me kind of zoom in here. So if we zoom in here, then this is what we're going to see. So it's kind of, so X is probably here. This is A, so this is X. But then, of course, if you choose a small enough epsilon, then you know, the whole kind of big interval from x minus 4 epsilon to x plus 4 epsilon is still going to fit entirely into AB. So the collection of these three even smaller subintervals is still going to sit inside AB. So this is true for every choice of x inside AB. So which tells us that yes, this is going to be open with respect to the second basis. So conversely, in order to prove that every set that is open with respect to B2 is also open with respect to B1, we need to choose that every basis set, so every element of B2 is open with respect to B1, right? So we choose any element of B2. So, and any element of B2 looks like a collection of three intervals. Each of them is of length 2 epsilon. Then we need to pick any point in any one of these three intervals. So we are going to pick some x. And then we need to show that there exists a basis set with respect to the first basis, so which is just an interval from A to B, with A and B being rational numbers. But then, of course, it is, so we can just pick A to be somewhere here, a rational number, and since between any two real numbers that there exists a rational number, it is possible. So we pick any B here, which is also a rational number, and then the interval from A to B, it contains x. And the interval from A to B, it sits inside this collection, this union of three intervals from x minus epsilon to x plus epsilon, from x plus 2 epsilon to x plus 4 epsilon, and from x minus 4 epsilon to x minus 2 epsilon, so which by definition means that the interval, this collection of three intervals is open with respect to the first topology. Okay, so we check the both things, it works out, and it means that these two topologies, although the bases are different, and the bases they even contain a different number of elements, so one is countable, the other one is uncountable, but they still define the same topology.